In this video, we're going to be discussing electronegativity, and we might get into bond energies, but my main focus is to talk about electronegativity. And so, what electronegativity is, by definition, is the ability of an atom to attract shared electrons from another atom. Its effect played dramatically on the atom's location on the periodic table. So, there's a basic trend that you have to follow, and that is the fact of as the atoms become smaller in size. So when we talk about the periodic trend with atomic radius, as you go up and to the right on the periodic table, as this arrow suggests, the atomic radius decreases in size. So that means that the upper right hand side where fluorine is, helium and neon gases, those elements are the smallest elements on the periodic table. And as you go further down to the left, those elements are the largest. Now, that is important because when we talk about electronegativity, the smaller the elements are, the more likely they're going to pull those electrons from their element when they're being shared in the covalent bonds. And so fluorine, being that it's on the upper right hand corner, is going to have the highest electronegativity value, and francium and cesium are going to have the smallest electronegativity values because they're largest and fluorine is smallest. We don't necessarily worry about the noble gases. We don't worry about the transition metals. Noble gases, for one, don't need any more electrons. They are already happy with what they have. Transition metals have their own set of rules, so we don't even worry about those. So it's really the main group of elements that we're going to focus on. And so the basic pattern again is that as you go up and to the right, the electronegativity values increase. Now, looking at this picture here, we can get an idea of what those values actually are for the elements. So in terms of fluorine is the most electronegative with a value of 4.0. Francium and cesium are both 0.7, and they have the lowest values on the periodic table. And so as we talk about the differences in electronegativities, when we deal with writing out compounds, whether they're being ionic or covalent, when we say ionic, we know there's a metal to nonmetal. When we say covalent, it's because we have two nonmetals bonded together. And those are defined by this table here in reference to the type of bond that they might possess. So these are just generic ranges that could be different if you look in your textbook or other sources, but it just gives you a general idea as to what type of bond you might be observing. Now that's not talking about the molecule, that's talking about the individual bond in between, let's say, a carbon and a hydrogen, or a carbon and oxygen. So when we deal with nonpolar covalent, the range just goes from 0 to 0.3. Polar covalent means you're going from 0.3 to 1.7. And then ionic bonds occur between 1.7 and 4.0. So if we were to, let's say, pick a carbon-oxygen bond, all right, so carbon is 2.5, and then oxygen is 3.5. So the difference between these two is 1. Well, that means that you're falling in the polar covalent category. Now, if we were to pick NaCl, if we look at Na is 0.9, and Cl is 3.0, that's going to give you 2.1 for the difference. All right, 2.1 represents an ionic compound, and so or an ionic bond specifically. So that's how we utilize. We look at the two atoms, we look at the electronegativity table, and then we figure out the difference between the two, and that difference, as you can predict what type of bond it is based off of that difference. So if we were to look at one more, let's say we look at hydrogen gas, H2, So hydrogen gas is 2.1, but since you have 2 hydrogen atoms only, that's going to leave you with a value of 0, because 2.1 minus 2.1 gives you 0. And so there's no difference. Therefore, hydrogen gas would be considered a nonpolar covalent bond. So another thing we can do is we can determine the polarity of a molecule. Now, it's not the same as determining the type of bond. The polarity of a molecule is really looking at the individual bonds and seeing how they relate to each other and if they cancel out or not. So if we take, for example, water, all right, so water has a Lewis structure like this, and we go and we look at the electronegativity table. What we see here is oxygen is further to the right than hydrogen. So what that means is that oxygen is more electronegative than the hydrogen, and so it's going to have a pull towards the oxygen. And so what exactly does that mean? Well, what that means is that since water is a bent structure, there's no way that these arrows are going to cancel each other out. And so you're going to have a net pull towards the oxygen, causing this molecule as a whole to be polar. So we don't really say it's polar covalent because that's talking about the specific bond. This bond is polar covalent. But the molecule as a whole is polar. And so when you have a polar molecule, if you notice the way this arrow is drawn right here, all right, so if you notice the way this arrow is drawn, if you look at the bottom down here, what that's showing you is that the electrons are being pulled from the hydrogen towards the oxygen, which creates a partial positive charge on the hydrogen, and then it causes the oxygen to have a partial negative charge. These symbols that I'm drawing here, this symbol is a delta symbol. What that means is a partial charge. It's not like an ionic compound where sodium is +1 permanently. These are still shared electrons in between the oxygen and hydrogen, but the bulk of the electrons are being pulled towards the oxygen, and so the density of the electron cloud would be a lot greater around the oxygen than the 2 hydrogens because it's more electronegative, and so it's going to pull those electrons closer to it. That makes it partial negative, where the hydrogens are both partial positive. So when we talk about partial charges, that's what we're referring to. So let's look at another molecule. Let's look at CO2. All right, CO2 has a Lewis structure that is drawn like this, and so now, yes, if we were to look at the carbon and oxygen bond, it's going to have a dipole pulling towards this oxygen, and it's also going to have a dipole pulling towards that oxygen because of the way the oxygen is more electronegative than the carbon. Now, it's like a tug of war here. So the carbon oxygens are opposite from each other, but they have the same pull. It's not a bent structure. CO2 is a linear structure, and that's important because the reason that this molecule ends up becoming nonpolar is because these dipoles cancel themselves out because they're pulling in opposite directions with the same force, and so it's not one or the other is going to have more over the other, so it just cancels itself out. So CO2 is considered to be a nonpolar compound. Now, if we look at another example, so let's say we have HCl. All right, HCl has a Lewis structure like this. The chlorine is more electronegative than hydrogen, so you're going to have this pull towards the chlorine. You can see that there's a lot of electrons around chlorine to begin with, and so that means that chlorine is a partial negative and hydrogen is partial positive. There's nothing to cancel it out, so this molecule is polar. So when you deal with these simple molecules that we've looked at here, the first thing you have to do is you have to draw the Lewis structure. The second thing to do is make sure that you understand the geometry of that molecule, and then you can start to just determine the type of polarity that that molecule might possess. So when we get into bigger molecules like CH3, CH2, OH, this would be ethanol. So when we look at this molecule, the Lewis structure is a little bit more involved, and so what we have to do is we have to focus on what's going on here in the Lewis structure. And we also have to observe that we have 3 different centers that show up here. And so those centers are important because each center has its own geometry, its own polarity. So when you look at the left side and you compare it to the right side, there is a difference between the two. And that difference is important because that's what makes this molecule what it is. So the left side, when I say the left side, I'm referring to this side here. The carbon hydrogens are all symmetrical, being that they all sort of cancel each other out. So the left side is nonpolar in terms of just the carbon hydrogens. The right hand side with the OH group, if you notice, there's 3 different elements that runs across here. So this is going to be a polar end. And this polar end is going to dominate these other carbons. Even though they're a little bit bigger in size, this oxygen is more electronegative than the other carbons and hydrogens. So this oxygen is going to have a stronger pull towards it. And so the whole molecule itself is polar by nature. So ethanol is polar. Now ethanol is alcohol. If you take water, which is polar, and this is something we get into in the future topic in a different course, chemistry 2 specifically. If you take water, which is polar, and you mix beer or alcohol into that water, it will dissolve. And that's because of the polarities are similar. The ethanol's polarity is polar, water's polar, and like dissolves like. And this is where this comes important, is that you have to understand the polarity, and especially when we start to mix different things together. Think about oil, for example, just to give you another example to go with this. Oil is just strictly carbon and hydrogens. And so oil, if you put oil into water, you know that it's going to float. It's going to be on top. And if you mix it, no matter how much you mix it, no matter how hot you get it, the oil will never mix with the water. And that's because oil is nonpolar and water is polar. And remember I said a few minutes ago, like dissolves like. So the polarities are important in reference to how and whether a solution will form. But in our case, all we're trying to do in this course is basically determine whether a molecule is polar. So the first thing you have to do, again, just repeating myself here, is that you need to draw the Lewis structure, figure out the molecular geometry, and determine then whether you have atoms that are more electronegative than the other atoms. And if you do those dipoles, and the dipoles are just the direction that the electrons are being pulled, do they cancel each other out? If they don't, then you have a polar molecule. If they do, then you have a nonpolar compound. So that's our discussion on electronegativity. The next thing that I'm going to get into is I am going to discuss bond energies. So bond energies will happen in a separate video. And so thanks for watching, and be looking for the bond energy video here shortly.